we are starting to look at titration procedures. You absolutely need to read your textbook. So, for titration procedure, we have our analyte, compound we want to analyze, being titrated by Titrant. This reaction goes to make some products, and we usually do not care much about these products. What is important requirement is that we have one only reaction, and coefficients A and B are integer, they are whole numbers. Better 1 or 2. We do not like big whole numbers. So this will be our first and most important requirement for the reaction to be used in titration. Second requirement, very practical. The reaction is fast enough to perform the whole procedure in 24 minutes. Better much faster. If your titration will take the whole day, you will not be able to use it. Next requirement, titrant solutions are stable and their concentrations can be easily established by simple procedures. And the last, there is an easy way to establish the endpoint of titration. So we have convenient indicator for this ending point. First requirement, one reaction with integer coefficients A and B. I have one reaction only. Side processes can be avoided. We expect deviation from stoichiometry to be less than 0.1% relative. So our yield is 99.9 to 100.1. Example of such good reaction. Strong acid reacts with strong base. Coefficients are whole numbers. Example of bad reaction. Strong acid reacts with weak base, but the reaction cannot go completely to the right. The acid is too weak to be titrated. Next requirement, solutions are stable and their concentrations can be easily established by simple procedure. Example of good solution, potassium dichromate. Experimentally, we know that it doesn't change in tens of years. Example of tricky solution, very common, sodium hydroxide. Must be protected from carbon dioxide from air. It is corrosive. You cannot store it in glass. Compound that you can weigh and dissolve to prepare a solution of known concentration without any standardization we name primary standard. The requirement for primary standard, purity at least 99.9, better 99.99. It is stable and easy to purify if necessary. It is convenient to weigh. I do not like weighing volatile liquids or gases. It's well soluble in your solvent, usually well soluble in water, and it is stable in solution. Now it should be non-toxic and non-expensive, very practical. Secondary standard, it's solution of known concentration which was established by titration of the primary standard. Now some examples. Potassium dichromate, solid salt, forms very defined crystals, easy to recrystallize. You can weigh it and make solution. HCl is a gas making solution of variable concentration. Weighing is possible, but very tricky. Usually it needs to be standardized. Sodium hydroxide, solid, attracts water, usually less than 90% of pure sodium hydroxide. Again, needs to be standardized. These two are example of secondary solutions. Devices we are using for titration are burettes. Well, when you think burette, very commonly you think about something like this. These days it's not true. More commonly we have burettes that are semi-automatic or automatic, and their design is absolutely different. Their tolerances are different, depends on manufacturer and on precision, and they are usually slightly better than Class A tolerances for glass burettes. We'll be using both of types. To make things easier, some titrators are completely automatic, so no human involvement in titration process itself. Still, if you put wrong sample, you're getting the wrong result. Next requirement, change of color. 10 points. So how we can stop? We need to change of color. We need to change of electrode signal. We may look for change of conductivity or something else. The place we stop titration, its end point. It is different from theoretical point when the reaction is completed. So we run titration, drop in liquid inside our titration flask, and at some moment color changes. That's how we stop. Again, these points should be as close as it is possible to equivalence point, theoretical point at which moles of titrant and moles of analyte are the same. Difference between endpoint and equivalence point must be less than 0.1% relative. So if I have exactly 1-to-1 ratio, I should stop somewhere between this and this. And this should be within tolerance of my burette. If I have my reaction completed to theoretical equivalence point, number of moles of analyte divided by coefficient A is equal to number of moles of titrant divided by coefficient B. Now, number of moles equal to molarity multiplied by volume of solution. So we can write molarity multiplied by volume instead of number of moles. Molarity multiplied by volume divided by coefficient A is equal to molarity of B multiplied of volume B divided by coefficient B. You can write it in shorter form. Now we can solve this equation for concentration of our analyte. In a very common cases, coefficients A and B are the same or even better equal to 1. Then our equation simplifies and is exactly the same as an equation for your dilution process. Let's look at example. I am titrating sodium hydroxide of known volume, 25 mils. I delivered it with my pipette, and I titrate it with HCl, hydrochloric acid, to make sodium chloride and water. Concentration of my sodium hydroxide will be, looking at this formula, concentration of my titrant, know it, volume that was necessary to run the titration, know it, divided by volume I delivered in my flask. Mils and mils will cancel each other, concentration will be in molarity units. Now, if I want to know how many moles and how many grams of my analyte are in titration flask, again, number of moles is concentration multiplied by volume. Number of moles of analyte is concentration of analyte multiplied by volume of analyte. But from our previous equation, we know that number of moles of A will be coefficient of A divided coefficient B. But now we have concentration of titrant by volume of titrant. Now, a mass is formula weight multiplied by number of moles. So mass of my analyte is coefficient at analyte, coefficient of titrant, formula weight of my analyte, concentration of my solution in a burette, volume that was necessary for titration. Now, we do not measure volumes in a burette with liters. We all do it in milliliters. So we need to divide by conversion factor of 1000 from liters into mils. So we are using volumes in mils. As a result, we need to divide by 1000. This formula is the main formula in all titration part of the class.